So far, we have treated problems where a data sample was used to discriminate between completely fixed competing hypotheses or to estimate free parameters of a given distribution. Now we turn our attention to the case where we would like to find out whether a single hypothesis without a completely defined alternative is true or not. So, the kind of questions we would like to address are following. So, for instance, we have two samples obtained at different times in an experiment, two that differ significantly from each other. Or is a signal in a spectral distribution significant? Can we describe a background distribution significantly better by a linear or by a higher order polynomial? Or even more specialized questions like, can we describe a sample of electron-positron reactions by quantum electrodynamics? To answer this kind of questions, we will have to set up a test procedure which quantifies the compatibility of a given data sample with a hypothesis. And the test has to provide a quantitative result which is used to judge how plausible or unlikely a hypothesis is. Now, a test can never prove the validity of a hypothesis, it can only indicate the problems associated with it. Now, usually a test is associated with a decision, accept or reject. We will not always attempt a decision, but confine ourselves to fix the parameters which form the basis for a possible decision. Before looking into such tests, I would like to give some definitions. So the first thing we want to distinguish between are single and composite hypothesis. Single hypothesis fix the population uniquely. So if we have a hypothesis denoted by H0, and the sample is drawn, so basically the hypothesis states that the sample is drawn from a normal distribution with zero mean and unit standard deviation. So this is an example of a simple hypothesis. Sorry, it should not say single, it should say simple. Now if the alternative is also simple, let's say which basically says that the sample is drawn from a normal distribution with mean equal to 5 and standard deviation 1. Then we have the task to decide between two simple hypotheses, and this is something which we have already treated. In such a case, there exists an optimum test, which is the likelihood ratio test. Composite hypotheses are characterized by free parameters. So if we just said that the sample is drawn from a normal distribution without specifying the mean and the variance, the mean and variance will be adjusted by the user, and the user will have to test whether the adjusted Gaussian is compatible with the data. So the hypothesis that we want to test is always H0. is also known as the null hypothesis. And in most cases, the alternative, which is H1, is the hypothesis that H0 does not apply. So then H1 represents an infinite number of specified hypotheses. After we fix the null hypothesis and the alternative, we must choose a test statistic. This is just a function of the sample values. And this must be chosen in such a way that the difference between the distribution and distributions belonging to H1 are as large as possible. Our typical test statistic is the chi-square deviation of a histogram from a prediction. Large values of chi-square basically indicate that something might be wrong with the prediction. Well, the next quantity that we must define, that before applying the test, we have to fix a critical region. Which will denote by capital K. Now, this critical region leads to the rejection of H0 if T is located inside it. Under the condition that H0 is true, probability of rejection of H0 is the probability that T belongs to K given H0 is alpha, where alpha is a number between 0 to 1, and it's normally a small quantity. And it is called the significance level or the size of the test. For a test based on chi-square statistic, the critical region is defined as chi-square greater than chi-square max, which is a function of alpha. And chi-square max fixes the range of the critical region. And to compute rejection probabilities, we have to compute the probability distribution function of the test statistic. In some cases it is known, but in other cases it has to be obtained by a Monte Carlo simulation. Now, after the test parameters are selected, we can apply the test to our data. If the actually obtained value of t, the test statistic, is outside the critical region, then we accept the hypothesis, otherwise we reject it. So this implies 4 different outcomes with the following a priori probabilities. And this brings us to a discussion of errors of the first and second kind. So the first one is that we're looking at an intersection of H0 and t belongs to K. The probability of t lying in the critical region given H0 is alpha, and this is what defines the error of the first kind. Which basically means H0 is true, but it gets rejected. The second one is an intersection of H0 being true, but t not belonging to the critical region. So the probability for t not belonging to K given H0 is 1 minus alpha. In this case, H0 is true and accepted. Third possibility is that the alternate hypothesis and t belongs to K. T belongs to K given H1. The probability is denoted as 1 minus beta. In this case, H0 is false because the alternative holds and H0 is rejected. Lastly, H1 holds but T does not belong to K. So the probability for T not belonging to K given H1 is beta, and this is what is known as error of the second kind. So in this case, H0 is false, but accepted. When we apply the test to a large number of data sets or events, then the rate alpha, the error of the first kind, is the inefficiency in the selection of H0 events. while beta, the error of the second kind, represents the background with which the selected events are contaminated with H1 events. Of course, for given alpha, we would like to have beta as small as possible. Now, for a reasonable test, we expect that beta is monotonically decreasing with alpha increasing. With alpha going to 0, the critical region K should be decreasing. While the power one minus beta must decrease and the background is less suppressed. For fixed alpha, the power indicates the quality of a test, that is, how well alternatives to H0 can be rejected. The power is actually a function of alpha. It's known as the power function. The tests which provide maximum power with respect to the alternative hypothesis for all values of alpha are called uniformly most powerful tests, UMP for short. Only in rare cases where H1 is restricted in some way, there exists an optimum, that is UMP test. If both hypotheses are simple, then the likelihood ratio can be used as test statistic to discriminate between H0 and H1 and provides a uniformly most powerful test. Now, the result of a test is that the hypothesis is either accepted or rejected. Now, in most practical situations, it is useful to replace this binary answer, one or the other, by a continuous parameter, which is known as the p-value. So p-value is a function of the test statistic, and it measures the compatibility of the sample with the null hypothesis H0. A small value of p casts doubt on the validity of H0. For an observed value, let's call it T observed, of the test statistic, P is the probability to obtain a value greater than or equal to the observed value under the null hypothesis. To simplify the definition, we assume that the test statistic is confined to values between 0 and infinity with a critical region, and its distribution under H0 can be some F0t. So in such a case, we can write P of t, so 1 minus integral from 0 to t, 0 t prime dt prime. We can replace the integral by the cumulative distribution function. Since p is a unique monotonic function of t, we can consider it as a normalized test statistic is completely equivalent to t. Next, let's introduce the notion of consistency and bias of tests. So a test is called consistent if its power tends to unity as sample size tends to infinity. Or in other words, if we have an infinitely large data sample, we should always be able to decide between the hypothesis H0 and the alternative H1. And we also want that independent of alpha, the rejection probability for H1 is higher than for H0. That is, alpha is less than 1 minus beta. Tests that violate this condition are called biased. Consistent tests are asymptotically unbiased. Now, when H1 represents a family of distributions, consistency and non-biasedness are valid only if they apply to all members of the family. Just in case that the alternative is not specified, a test is biased if there is an arbitrary hypothesis different from H0 with rejection probability less than alpha, and it is inconsistent if we can find a hypothesis different from H0 which is not rejected with power unity in the large sample limit. So now, after all this discussion, we can shift our focus to goodness of fit tests. So goodness of fit tests check whether a sample is compatible with a given distribution. In natural sciences, goodness of fit tests usually serve to detect unknown systematic errors in experimental results. So for example, when we measure the mean life of an unstable particle, we know that the lifetime distribution is exponential, but to apply a goodness of fit test is informative because a low p-value may indicate a contamination of the events by background or problems with the experimental equipment. So in this context, let's first see how do we interpret and use p-values. So we introduced p-values in order to dispose of a quantity which measures the agreement between a sample and the distribution of the test statistic. So small p-values imply a bad agreement. Since the distribution of p under H0 is uniform, all values of p in this interval are equally probable. When we reject a hypothesis under the condition p less than 0.1, we have a probability of 10% to reject H0. The rejection probability would be the same for a rejection region p greater than 0.9. The reason for cutting at low p values is the expectation that distributions of H1 would produce low p values. So p value is not the probability that the hypothesis under test is true. It is the probability under H0 to obtain a p value which is smaller than the one actually observed. P value between 0 and p is expected to occur in the fraction p of experiments if H0 is true. As a first and probably the most elaborate example of goodness of fit tests. Let's introduce the concept of chi-square test. So consider a sample of n observations which are characterized by the values xi of a variable x and prediction f0x of their distribution. We subdivide the range of x into b intervals to which we attach sequence numbers k. So the prediction Pk for the probability that an observation is contained in interval k is given like this, and we impose that the sum of all these pk's should be equal to 1. So the integration basically extends over the interval k. The number of sample observations in the kth bin has to be compared with the expectation value. Now to interpret the deviation dk minus n times pk, we have to evaluate the expected mean quadratic deviation delta k square under the condition that the prediction is correct. Now we know that distribution of observations into bins follows a binomial distribution, and this implies that delta k square is given by n times pk multiplied by 1 minus pk. Usually the observations are distributed in typically 10 to 50 bins, so the probabilities pk are small compared to unity, and we can omit the expression in the bracket. For small pk, delta k square is simply n times pk. Now we can normalize the observed to expected mean quadratic deviation. That allows us to define chi k square as dk minus n pk square by npk, and then we sum over all bins. Basically, the final calculation will give us that expectation of the kth chi-square is approximately 1, and that of the total chi-square is approximately b. Now, if the quantity chi-square is considerably larger than the number of bins, then obviously the measurement deviates significantly from the prediction. A significant deviation to small values, the chi-square is much smaller than b, even though considered as unlikely, is tolerated because we know that alternative hypotheses do not produce smaller chi-square than h0. Now, with the chi-square distribution, we associate the parameter, the number of degrees of freedom, this is equal to the expectation value, and this will equal number of bins minus 1. Now, originally we had set the expectation value of chi-square as approximately b, but this relation overestimates chi-square slightly. A smaller value, b minus 1, is plausible because the individual deviations are somewhat smaller than 1. So in the limit of a single bin, the mean deviation is not 1 but 0. So in some cases, we have not only a prediction of the shape of the distribution, but also a prediction of the total number of observations. Then the number of entries in each bin should follow a Poisson distribution with mean n0 pk. And we basically have to make the replacement that chi-square equals in this case the number of degrees of freedom, which is the expectation of chi-square, equals b. In experiments with low statistics, the approximation that the distribution of the number of entries in each bin follows a normal distribution is sometimes not justified. And the distribution of the chi-square quantity, as defined in the above expressions, is not very well described by a chi-square distribution. Then we have the possibility to determine the distribution of the chi-square variable under H0 by a Monte Carlo simulation. The chi-square comparison becomes a test if we accept the theory, the theoretical description of the data, only if the p-value exceeds a critical value. that critical value being the significance level. Alpha, and reject it for p less than alpha. Then the chi-square test is known as the Pearson test. Now, in general, there is no rule for the choice of the number and width of the histogram bins for the chi-square comparison. But we must note that the chi-square test loses its significance when the number of bins becomes too large. So to estimate the effect of fine binning for a smooth deviation, we consider a systematic deviation which is constant over a certain region with n0 entries and which produces an excess of epsilon times n0 events. If you partition the region into B bins, would add to the statistical chi-square in each single bin basically chi-square becomes chi-square plus chi-s square. The second term would be given by epsilon n0 by b square times n0 by b So basically for B bins, we increase chi-square by epsilon square times n0, which is to be compared to the purely statistical contribution, which is in average equal to B. The significance is the systematic deviation in units of the expected fluctuation. So square n0 by 2b decreases with the square root of the number of bins. A fine binning is only recommended if the deviations are considered which are restricted to narrow regions. These are rare in usual applications. Rather, we have systematic deviations produced by non-linearity of measurement devices or by background, and which extend over a large region. Then wide intervals are to be preferred. If we generalize to arbitrary measurements, so arbitrary measurements yk with mean square error delta k square. theoretical predictions, which will denote by Tk, we compute the chi-square. So chi-square basically follows a chi-square distribution of n degrees of freedom. Our necessary condition for the validity of the chi-square distribution is that the uncertainties follow a normal distribution. For a large n of individual measurements, the central limit theorem applies, and we can relax the condition of normality. Then chi-square is approximately normally distributed with mean n and variance 2n. I must note delta square is to be calculated assuming that the theoretical description which is to be tested is correct. This means that normally the raw measurement error cannot be inserted. For example, instead of ascribing to a measured quantity an error delta k prime, which is proportional to its value yk, a corrected error should be used. Sometimes extremely small values of chi-square are presented. The reason is, in most cases, an overestimation of the errors. The variable chi-square is frequently used to separate signal events from background. To this end, the experimental distribution of chi-square is transformed into a p-value distribution. And in this situation, it is not required that chi-square follows the chi-square distribution. It is only necessary that it is a discriminative test variable. Lastly, let's look at the chi-square test for composite hypothesis. In most cases, measurements do not serve to verify a fixed theory, but to estimate one or more parameters. To fit a curve, theta is a vector of parameters. So we want to fit this to measured points. Yi with Gaussian errors. We minimize So we minimize this chi-square with respect to z free parameters. Theta k. It is plausible that with increasing number of parameters which are adjusted, the description of the data improves and chi-square decreases. In the extreme case, where the number of parameters is equal to the number of measured points or histogram bins, it becomes 0. The distribution of chi-square in the general case, where z parameters are adjusted, follows a chi-square distribution with n minus z degrees of freedom. And this expression for chi-square, if we set zi equals yi minus t of xi comma theta by sigma I, we can interpret chi-square, which is sum from I equals 1 to n zi square, as the squared distance for point z with normally distributed components from the origin in an n-dimensional space. If all parameters are fixed except one, let's say theta 1, which is left free and adjusted to the data by minimizing chi-square, let us set the derivative with respect to that parameter theta 1 equal to 0. Basically tells us if t is a linear function of the parameters, an assumption which is often justified at least approximately, and the derivatives are constant. And we get a linear relation of the form C1 Z1 plus C2 Z2 is Cn Zn equals 0, which defines a n minus 1 dimensional subspace. So hyperplane containing the origin of the n-dimensional Z space. Consequently, the distance in Z space is confined to this subspace and derived from n-1 components. So for Z parameters, we get Z constraints and n-z dimensional subspace. The independent components of this subspace are called the degrees of freedom. And this is precisely the number of degrees of freedom of the chi-square distribution. So obviously, the sum of f squared components will follow a chi-square distribution with f degrees of freedom. Now, when the number of entries per histogram bin is small, the approximation that the variations are normally distributed is not justified. Consequently, the chi-square distribution should no longer be used to calculate the p-value. Nevertheless, we can use this in this situation. We can use the sum of quadratic deviations chi-square as test statistic, and the distribution has to be determined by a Monte Carlo simulation.